So, hi everyone. Thanks for having me here. My name is David Almog. I'm a four-year PhD student in Kellogg, in Northwestern. And I will present my project on AI oversight and human mistakes, evidence from center court, with my co-authors Roman, Lionel, and Daniel Martin. So for this talk, I'm going to skip the slides about how good is AI. I don't think I need to convince this crowd about that and how it's already performing as good, if not better, than some professionals. So the question I'm going to focus is, it's kind of motivating to think that a process that involves AI and humans has the potential to yield better results than either of them acting alone. But there's multiple ways of designing that process. Something we're going to focus is, let's decide who gets the final decision rights. Like, that's one way of shaping these processes. A more studied approach in the literature so far is when humans make the final decision, most commonly after receiving AI recommendations. A very important skill that needs to be executed here is discretion, like knowing when to follow your private information and knowing when to actually follow recommendations. And this is work that has been done, like we have evidence from hiring and promoting. We have evidence from radiology, like what Alex presented yesterday. We have evidence from courts and sports, as you will see following my talk. Less studied approach is what happens when we provide AI with the final decision rights. Like, that's what we call AI oversight in this case, and humans may be overruled if AI believes that they are making a mistake, right? So we are already starting to see that, like computer vision systems, like to steer car backs into lanes, like if you deviate a little bit from your car, like from your lane, the car goes back immediately, like financial trading and energy management, like are examples that already are showing this kind of oversight and overruling from AI, like a very recent paper showing that humans may have additional information about fashion trends and they can decide pricing and discounts, but it will only work if there's an AI force behind that overrules when there's like clear source of biases. What happens here is that what used to be discretion, like a very important skill when the human had the final decision rights, now that force changes a lot. Like now it's about shame, pride, embarrassment. So these are new forces that we need to understand better when we apply this type of decision processes. So why to keep humans in the loop? Like, there's a lot of reasons. Like there's social reasons, like humans could perform better as well, like in edge cases. Like there's also private information humans may have, like there's labor market concerns. So it's not that easy as just take out humans. Like I'm going to show examples from tennis. Like I'm going to anticipate, like it's been 20 years since Hawkeye has been playing a role in tennis, and it took 20 years and a pandemic for almost a perfect technology to start replacing humans. So I don't expect to see judges and doctors being replaced anytime soon. So what I'm going to do today is going to show a little bit of how important it is to assess the full impact of AI oversight and how it requires to understand whether its presence alters human decision making. So once you introduce AI oversight, humans are not going to stay the same. So you need to assess how humans react upon this. So the two things I'm going to focus are humans going to have an attentional response, and second one, like the way we introduce AI oversight, will that introduce some asymmetries as well? Okay, so let's go to the context. Hawkeye is introduced in 2006 in the Miami Open. It's used for the first time. How it works is that players have the ability to challenge calls, and the calls are like displays in a big screen, and what Hawkeye makes is like using a lot of cameras and using information about the speed and trajectory of the ball and like the spin of the ball as well. They make a 3D prediction that's shown to everyone in the court, and if the decision from the original decision from the umpire is wrong, then it's corrected most of the times. The average error of Hawkeye is very, very small. It's just 3 millimeters compared like to diameter of the ball is 67, so it's very precise. And it's not ground truth, but the ATP and we as well will consider it ground truth for this exercise that we're going to present today. What we're going to assess is the collective performance of the umpire crew. Like there's up to 10 umpires in the court. Like there's one in charge of every single line, and there's a chair umpire. So as a line umpire, all you have to do is focus. You have to decide whether the ball is in or out. That's mostly all your job. So what are the advantages of this empirical setting? Why tennis? Like this is a great context to study this question. It's one of the pioneering applications of AI oversight in a work setting, like not only in sports, but in general. There's great data, like they have like this testing period where they were collecting data already, but there were no challenges. Like it was only shown in the broadcasts. So we have 7 tournaments, like 100 matches, like the precise location of the ball before there were any challenges available. And then we have 20 tournaments with challenges. There's no clear source of private information, like in some cases, like with judges, like that's another very common example in economics. That's a problem. Like you never know what the judge knows. So it's hard to make inference about whether they're making a mistake and some other things. And as I mentioned, like the decision problem is extremely simple. Cannot be simpler than this. It's just a binary action, like the umpire calls it in or out, and it's a binary state, like where the ball bounces actually, in or out. Like so, these are great advantages. I think this is a great setting to study the question. What makes Hawkeye interesting? We can allow to study the 2 questions I introduced in the beginning, like, do we see an attentional response from the umpires? Like, are they relaxing knowing that their mistakes can be corrected? Or are they paying more attention because they know their mistakes are being observed and corrected in public? So these are big questions. Like, when you think about judges, like, do you think they would relax if something like this would be implemented? Or would they be really mad that some source of AI is overruling their mistakes and potentially in public? The second question, do we see any distortion on the type of errors? So we can argue that ex ante the type of errors in tennis were similar, like calling something in when it was out or out when it was in was fairly the same. It's not anymore when Hawkeye is introduced. So there's one type of error, like calling a ball in when it's out. That's the same. If it's overturned, then you just change the call. But the problem is when you call a ball out when it was originally in, you stop the point. So there's no way back. And on top of that, like the umpire has to decide arbitrarily if the receiving player had a chance to reach the ball. So it involves arbitrary decisions from the umpire and infuriates players. So this is a now more costly mistake that it didn't used to be the case. There's recent controversies like this is happening. People hate this type of mistakes. If I have time, I will show you a video of how miserable the umpire's task can be when Djokovic is shouting at you. Like, it's really hard. So we're going to see what happens. This is the empirical strategy I use. I regress incorrect call or mistakes, and I have a dummy of whether it happened in a tournament with challenges or not. I also control for point characteristics and match characteristics, like the type of tournament, the speed, the moment of the game, the stage of the tournament. And the first thing that shows up is that if we use the entire sample, we see an 8% mistake reduction. They go from making a 13% mistake rate to is reduced by 8%, by 1 percentage point. Then I'm going to split the sample in 2 different ways. First, I'm going to focus in balls that are within 20 and 100 millimeters. The not so hard ones, like the within 20 are extremely hard. But let's focus first on these ones. Like if we divide by serves and by non-serves, we see a very, very stark improvement. Like they reduce mistakes by quite a lot. Now, why I'm dividing by serves and non-serves? Not because, I'm a tennis fan and I'm interested in aspects of the game. There are 2 very different cognitive tasks. Serves go faster, but also with serves, the umpires know where the ball is going to be bouncing. Like they can anticipate the bounce. So it's also like they are more attentive, like it's harder to get distracted.
Can I just ask more of a practical question here? So Hawkeye could just replace the umpires.
Yeah.
So is the point of this work that let's imagine that there's a resource allocation problem where Hawkeye can't be built at every stadium, and or tennis stadium. So now, do umpires get better in situations where Hawkeye is not there? Is that your question from a practical point of view, or you just want to know how people are learning?
My practical way, like the way I envision what we can learn from this is in situations where you don't have a technology that's way better. Like
that's what I'm asking. So you're talking about, do humans get better in situations where technology can't be there?
No, do humans get better in situations where technology is there?
I'm talking about after your study's done.
Yeah.
If every stadium had Hawkeye, don't need humans. Get rid of the humans. So this question's not relevant. It's only relevant in situations.
No, it is relevant because I don't care about tennis. I want to learn how humans react.
Well, that's what I'm asking you.
Yeah. I want to draw inference about how humans might, like how judges and doctors may react. But tennis is the perfect empirical example to study. Yeah, of course, if we care about tennis and all you care is about efficiency, replace them. Like,
right.
Yeah. But when we look at the hardest goals, they get better in non-serves, but serves, the tasks where they are pushed the most, they get worse. Why? Like, they are getting worse in serves. It was already a very difficult task, but there's something fascinating happening. Like, they're getting better overall, but in serves they're getting worse. And what happens is, I'm going to show you the raw data. Here I put the average mistake rate by bins of 20 millimeters. So this is within 20 millimeters out, within 20 and 40, and so on, and in by 20 to 40. The blue line is the mistake rate before Hawkeye was introduced, and the red line is the new one. We can see how, for most of the dots, they are below, so they are making better decisions. But what happens is, around the line, they are shifting the type of errors. They are willing to sacrifice making a lot more of the not that costly error to improve a little bit in the costly error, the one that's going to get players infuriated. So we are seeing both happening at the same time. They're getting better, but also they're substituting one type of error for another one. And in serves in particular, they gain a little bit of reduction in the very costly error at the expense of a very big increase in the not so costly one. That's why they get worse, actually. And the raw data pattern that we observe sustains once we control for all the things I mentioned we could control. So these are the estimates. We can see the shift, like they get more mistakes of calling something that was out as in, but they improve a little bit more about the balls that are in and they were used to call out. And overall, after 20 or 40, like, they kind of improve as well. What drives this shift? Like, what happens is that when the ball bounces really, really close to the line, they decide that they are going to call it in more often. Like, that's why the type of error shifts is happening. Like, when they're very uncertain about what's going on, they shift to call the ball in from 42% to 49%. So, in part, like the last part of the paper, we make a model of rational inattentive umpires with the canonical model of Shannon and entropy cost of paying attention. We structurally estimate what's going on, and we find that the umpires behave as if they care twice as much about the type 2 errors when under AI oversight. So the costly mistake is now twice as unpleasant to make as it used to be. Just to recap, the introduction of AI in professional tennis improved tennis umpires' performance in certain aspects of the game, but the implementation of oversight instruments may change incentives and give rise to like reactions in behavior. Like, for example, in this case, lean toward the less costly mistake from the perspective of the umpires, not necessarily from the game or from the ATP. So it kind of distorts incentives as well. So we encourage future research to be conducted in experimental settings to understand better, like what are the human and AI costs and explore the mechanisms better. So I'm happy to take questions from here. Okay. Yeah.
I've studied the long-term and short-term impacts, so maybe they'll be diligent, once the camera is initially installed. But it's difficult to keep up that level of diligence, let's say, fast forward 3 years.
Yeah, so here we're limited by the data we already had. Like it was 1 year before, and we have 3 years since 2006, that's 2006, 2007, 2008. What we see is that most of these effects happen after a year. So maybe like being shouted by Djokovic at your face, it's a learning experience that makes you eventually call more ins and outs, and like start shifting takes a little bit of time.
Yeah. You think it'll actually make the game better where there's more sense of fairness because there have been issues with some players and with some judges,
Yeah.
right? Like,
I don't know, like you have, on one hand, like you have Federer, for example, one of the best players ever. Like he commonly goes out and say that Hawkeye made umpires lazy, which is not the case. I'm showing that's not what's happening. But at the same time, it happens that in our data, we observe that Federer is the world challenger. Like he's really bad at challenging. So maybe that has to be with that. Like it introduced another aspect of, like he's great at everything but that. So yeah, as you might hear, like they are starting to displace referees entirely in some tournaments. Like there's only a chair umpire, and yeah, but it took a very long time and almost a perfect technology. So this is what it takes to displace humans. I believe so. Like yeah.
I think the same thing would happen with baseball.
Yeah, I mean,
Sports.
I think it's starting to happen. There's a lot of things to consider. Like in stadiums, it's incredibly exciting to watch the replay. So it also adds a lot more things. I don't think what they are maximizing is accuracy because they will have displaced them sooner. But if fans like to see umpires being overruled, then that also plays a role. Yeah.
So you didn't tell us about the details of your structural model. Let me say why I'm interested.
Yeah, yeah,
question,
for sure.
Let me extend on the question I asked before. So this is a situation where humans can be replaced. Maybe you want to generalize your findings to situations where humans can't be replaced right now. So I'm just wondering, how generalizable do you think your findings are? And do we all need to be thinking, and I'm saying this in a positive way, to build structural models? Because you don't have data from all these other counterfactual situations, but maybe your structural model is going to allow you to generalize. So how are you thinking about that? Like here, the umpires know that if they continue to be bad, they will get replaced by Hawkeye. So they have a model of attention. They have a huge incentive to pay attention. Maybe in other cases, people don't.
Yeah, that's exactly related to the first question, whether they pay more attention or not. I think that what can be generalized from this is that it takes a lot of public and a shaming mechanism to actually induce more effort. If this would be private, I believe we wouldn't be getting these results. That's what I want to take out of this. Like, you're going to correct judges and doctors in private, they're going to be lazy.
Thank you. That was us. Thank you.
Let's take other questions offline. Thank you.
Hi, everyone. Thank you for coming to this talk. My name is Sungwoo Cho, and I'm a sixth-year PhD student at UCLA. I'm very excited to present my paper, The Effect of Robot Assistance on Skills. And I think this will be my last presentation with my UCLA affiliation because I'll be graduating in about 3 weeks. So in recent years, there has been growing concerns surrounding the potential impacts of industrial robots and AI technologies that we've seen in the past couple of days that might displace humans from some works. But instead of displacing humans, numerous robots and technologies actually collaborate with us, potentially improving and enhancing our work. And yet, in the presence of reliable technological aids like the autopilot system for pilots or the AI like ChatGPT, workers may decrease their cognitive engagement with the work task, potentially contributing to individual workers' descaling. And these technological aids have proliferated in recent years, not only in the workplace but also in our daily lives that we use, such as ChatGPT or GPS system navigating around the cities of Philadelphia, for example. And other technological aids exist in everywhere. But even in a world where robots are readily available, I believe that the human capital without robots are still going to be essential for cases in emergencies where Captain Stellenberger landed the plane after the plane experienced a malfunction due to a bird strike on the Hudson River, or for the industries that require human oversight, like the bail judges, for example. So in this paper, I ask a very broad question of how does working with robots change human capital? So first, I ask what are the gains from adopting robot assistance technology on the assisted workers? And second, I ask whether the workers lose skills when they are assisted by a robot, but then lose access to this technology. Relatedly, I ask whether longer work duration with robot assistance worsens the skill depreciation, and whether the workers bounce back if they return to the task without assistance over some time. So I take the setting from tennis court, away from tennis court now to the baseball field, and I study the setting of the automated ball strike system in the baseball setting, where the umpires are assisted by this technology, making a ball strike decisions. So what the system does, it's exactly similar to the Hawkeye system. So it has a sophisticated hardware like the Hawkeye system, and an advanced algorithm system that tracks pitches and helps the umpires calling pitches, the balls or strikes. Empirically answering this question of whether robot assistance worsens human skills is empirically challenging. However, baseball setting provides important advantages. First, I have a new granular data set, so I get to observe the worker-specific usage of technology, so I know exactly which umpires were assisted by a robot and those umpires who weren't assisted by a robot. Also in this setting, like tennis, I observe very granular data, where I observe the pitch location and the decisions made by the umpire and whether it is correct or not. Also in this setting, I have a substantial variation in the implementation of the robot technology to identify the benefits and costs of the robot assistance system. So I observed that I exploit the staggered adoption of the robot assistance technology and also the umpires moving across leagues. So there are 11 different minor leagues in the system, so the umpires can move across these leagues. So I get to observe umpires before and after having been assisted by a robot, as well as with and without the robots in this time period. So to preview some of the results that I believe I don't have enough time to go over in this 30-minute presentation, first, I find that the umpires, when they're assisted by a robot, they improve human umpires' accuracy by almost 7%. Also, the skill distribution compresses, with the low-skilled umpires benefiting much more from this technology. More interestingly, what happens when the robot is removed or the workers lose access to this technology? The umpires lose skill by about 2.1% relative to the pre-assistance period. A 2% decline here is roughly equal to taking a median umpire of the skills distribution down to the bottom 5th percentile. So it is a very large effect. Interestingly, the skill distribution also compresses here, with the high-skilled umpires losing more skill now. And also, I find that the workers or the umpires who work with the robot assistance for longer duration, they suffer larger depreciation. And also, the umpires who are exposed to robot assistance technology for a full season, they do not quickly bounce back, and they don't fully recover within a season of return to the work. I argue that this loss is not entirely due to time off work using a separate treatment, and I also find that the umpires lose skills in a related task that umpires perform. So I view my work as contributing to several large strands of literature on robot adoption and skill depreciation. Overall, past literature has generally focused, in labor economics at least, on the displacement effects of the robot technology, and I believe I'm one of the first to study what happens to the workers when they're assisted instead of displaced by robots, and what happens to them after they lose access to this technology. So let me introduce the setting and the data. So human umpires are standing physically behind the plate and making the ball strike decisions. And the umpire must solely make a decision on every thrown pitch that is not swung yet. And these decisions are in split seconds, so they are subjective to human judgment and potentially some errors, potentially undermining accuracy, fairness, and consistency in determining the outcome of each pitch. The decision guideline for the umpire is the strike zone. So if a pitch crosses this strike zone, the umpire must call it strike. If they miss the strike zone, they must call it ball. So it is the only guideline for the umpire that they use. And the strike zone is defined as an imaginary rectangular region over the home plate that extends roughly between batter's shoulders and kneecaps and has a dimension of about 20 by 25 inches. So despite the umpire's efforts to strive for consistency and high accuracy, they sometimes make mistakes. Not quite a lot of times, but sometimes make mistakes. But that results in a Twitter feud on a lot of fans don't like it on a controversial calls and stuff. So, so the Major League Baseball decided to experiment with something called the automated ball strike system that they like to call it the robot umpire that provides reliable assistance in ensuring the accuracy and fairness within the game. So how does the system actually work? When a pitch is thrown from the pitcher from the mound, the system, using the multiple cameras placed around the stadium, like the Hawkeye system, tracks the pitch and points the pitch location as it crosses the strike zone, and then the call is communicated through an earpiece like an AirPod to a home plate umpire standing physically behind the plate, and he makes the decision himself. So the robot implementation, the experiment started in the Single A Florida League in 2021, and the success in the experimentation led to an expansion throughout the minor league system. In 2022, AAA Pacific League implemented it, and in the last year, all of the AAA leagues implemented this technology. So let me introduce the data. So I have a universe of the major league and minor league pitch level data from 2017 to 2023 seasons. I have a detailed pitch characteristic. Importantly, I have the X and Y pitch coordinates as they cross the strike zone, and I have the umpire's decision. So I have about 8.8 million called pitches from 62,000 games with about 700 umpires. So again, the main outcome of interest is the skill, or measured as decision accuracy, that uses the pitch location, the strike zone, the dimension of the strike zone, and the umpire's decision to make this decision accuracy measure. So let me introduce briefly what my empirical strategy is and show some of the results. So there are 11 different leagues in the minor league system, and let me take umpires that worked in the AAA Pacific League in 2022 as an example that implemented the robot assistance technology. So I get to observe where these umpires worked in 2021, which I call the pre-period, and I observe them in 2022 when they're assisted by a robot, and I call that with the indicator variable DIT robot. And in the following year, in 2023, I get to see them in other leagues if they move. For example, if they move to Major League, and they now no longer have access to this robot assistance technology. So my empirical strategy exploits a staggered adoption of the robot assistance technology and also the umpires moving across leagues in a difference in differences framework. So the main outcome of interest YIT is again, decision accuracy measured as whether a pitch is correctly called or not. And I estimate the effects for two separate periods. The DIT robot, the indicator is for the period where the umpires are being assisted by robot, and DIT post-robot is now the cases where umpires are no longer being assisted by robot, but after having been assisted by robot. Therefore, the delta 0 is the coefficient that measures the relative performance of umpires using the robot assistance technology, and delta 1 is the main object of interest as it captures the effect of the robot assistance technology on human umpire skill after having been assisted, but no longer having access to this technology. The main identification assumption of this empirical design is that the conditional on the controls and the fixed effects, that the umpires who are moving across leagues are not on the differential trends as the umpires who are staying on the leagues. So to partially test for this assumption, I also implement the event study design to test for any pre-trends, and DIT, the indicator variables DITK, specify that the umpires are K month away from the specification or from the implementation of the technology, and I check that the coefficients delta K prior to the implementation are not statistically significant from 0. So first, as how do the umpires change with the robot assistance technology, and I show you the event study versions of my results. So first, when the umpires are being assisted by robot, they enjoy higher precision and accuracy, and in fact, the accuracy in these games with robot increased by about 6.4 percentage points, or roughly about 7%. However, after having been assisted by robot, but now no longer having the robot assistance technology, the accuracy drops below the pre-assistant period by about 2%, which again is the size of the effect here is about taking a median umpire down to the bottom 5th percentile, so it's a very large effect. I also conduct various heterogeneity analysis. Something to highlight, I find that the high-skilled umpires lose more skill following the robot implementation, and also the longer work duration with robot assistance technology worsens skill depreciation. I also conduct several robustness checks. My empirical strategy exploits the umpires moving across leagues. So it might be due to the fact that the control, like umpires being compared to, if the umpires moving are systematically different from the umpires who are staying, that might bias my results. So I check by using different control groups and largely replicate the same results. Next, I asked whether the robot effects are actually the same as time away effects. So I used a separate treatment of COVID-19 pause where the Major League Baseball season was delayed and shortened but continued, whereas the minor league season was entirely canceled. So I used a difference in differences framework, comparing the minor league umpires who abruptly experienced a year-long unemployment in their career to the Major League umpires who didn't. And I find that the umpires returning from the COVID-19 pause actually do lose skill, marginally significant at the 10% level. However, the size of effect is much smaller than the robot effect. So I argue that the umpires who have been assisted by a robot suffer larger skill decline, and this is not driven by the time of work. Finally, I also asked whether the other skills are affected by the robot implementation. A question you might have here is that if the umpires are now no longer spending any effort making the ball strike decisions, they might be allocating this effort to somewhere else where we might see a skill increase or decrease. Unfortunately, the home plate umpires, the main task of home plate umpires is calling balls and strikes. But what I get to observe is the first base umpires, after having been assisted by a robot, as a home plate umpire before, whether they suffer a loss in skills in their related skill. So the main task of the first base umpires is determining whether base runner is safe or not, and they have a replay review like the Hawkeye system mechanism to correct for these errors. And I find that the umpires who have been previously assisted by a robot, they also suffer a decline in this related skill. So to conclude, in this paper, I studied what are the effects of the robot assistant technology on human umpires or human skill. And I find that the umpires suffer a large skill depreciation after having been assisted by a robot. Thank you.
We have time for maybe one quick question.
Thank you for a very nice study. So I guess you alluded, you looked at the response by players, I guess. So I'd love to hear more about how particular pitchers change their plays.
Right, that's a good question. So players do also adjust their strategy, pitching strategy, based on this robot implementation. I view players as some sort of co-workers where the umpires are now being replaced by robot. So players do adjust their behaviors to target different area of the strike zone where they're now more favorably going to be called by the robot umpire instead of the human umpire. And these effects do not persist as long when they return to the league without robot umpires.
Okay, good morning, everyone. My name is Steve. I'm currently a postdoc from UIUC Gies College of Physics. It's really my great pleasure to present our paper to this great audience here. And our title is Backfiring AI Deployment in Workplace. And it's a joint work with Manmohan Asari and Narayan Ramasubbu. So as has been talked a lot since these 2 days, we witness a drastic increase in AI adoption, such as shown by this latest survey on LM adoption here. About 40 to 60% of firms are considering using AI, or they are already starting to use in their workforce. So here are some common and popular practice of AI adoption use case. The one on the left is basically offering real-time feedback to employees so that they can have access to the best practice in the organization. Well, the one on the left is we're providing business know-how to almost everyone in the organization. So all these cases can be considered as a conduit of knowledge transfer that enables knowledge sharing among all the employees, especially towards those who don't possess those knowledge before. So, and as we have heard since yesterday, these types of system have high potential in improving the productivity. But we also heard about there can be lots of obstacles, right? Such as lack of complementary assets or user aversion to our algorithm. So our question is if we can remove most of these type of obstacles, does that mean AI adoption will definitely lead to a productivity increase? Will there be other like organizational factors that CTOs and CIOs has to be aware of? So thinking along this line, one organizational factor and policy that came to our attention is the firm's reward policies, because that has been shown to have a huge impact on like employees' motivation at work. And especially given the pay for performance scheme is the most popular kind of reward policy among all like US firms. So our question is, what's gonna be AI's impact on productivity and firm's profit if the firm has already have this type of scheme in place? And different to most of the studies here, we'll use a game theoretical model to answer this question at a relatively higher level. So let me just quickly summarize how we model the firm and the interaction between the employee and the AI. So we think like if the employees are definitely different among this group, and to capture the AI's different impact on employees, we think each employee, they will possess two different types of skills, either tangible or intangible. So as you can tell by the name, it's basically the difference between these two skills is whether the AI can learn these skills. So we know that since the past 18 months, the line between these two skills has been like redrawn like frequently, but still there are things that AI system couldn't learn yet. And then for each skills, there can be a high type or low type. So which means we'll have 4 different types of employees in the organization. So for example, the HL type in the right lower right corner are the employees who are really strong in their tangible skills, but not so much in the intangible ones. And then we have parameters to describe the percentage of employees, such as PD and PI here. Then the employee's important decision is basically how much effort or how much labor input they want to put in their work. So their effort will decide their production level, as well as how much they can earn, as well as the cost they will experience. And note that here the salary rate is the component that reflects the firm's reward structure. And here we consider a case where the firm will introduce a bonus that is basically mapping the pay for performance schemes that is happening in the real world. So which means the firms will introduce 2 different levels of salaries. If the employees are belonging to the groups that are performance at the top, they will receive a bonus rate. And then the most important part of our model is how AI gonna affect the employees. So we introduced this AI efficacy F. It is the rate at which the AI will improve the tangible skills among employees. And more specifically, in our base model, we only consider the case AI will mainly help the type, which means this is the original skill gap. Then after we introduce the AI, the lower level for the ability will be improved at this rate F. So now, after we solved for employees and the firm's decision, let me report the most important result. That is the firm's overall productivity and the profit can actually drop after AI deployment. And this will happen especially if the ability level for the low type tangible skills is not very different from that high type. And when we have a higher proportion of HL type. So visually, we can see that under certain business cases or parameter range, that in the upper right corner, the firm will experience a performance drop. So just to quickly recall, our model has already abstracted away the common adoption obstacles that has been talked about, right? So then why the firm still couldn't benefit 100% from AI? To answer this question, let's first look at what the reward scheme is doing on employee incentives. So here is a possible performance ranking among 4 different types of employees. And what we find is when the firm decides to say, let's promote the top 2 groups of employees, give them a bonus. What that's gonna do on employee incentive is that it's gonna intensify the competition for the second place. And the employees, for example, the HR types here, they're gonna put in extra effort just to ensure they are being promoted. So that's the first thing. The second is what's AI gonna do on their performance ranking. So a possibility is, because right now the AI is going to help the low type on their tangible skills. That is, AI will help the LH and the LL type. So it's very likely that after AI, we're going to observe a performance ranking flip. That is, right now it's the LH type going to rank at the second place. So keep this briefly in mind, and let me break down the overall impact of AI on productivity. So here is first is the ranking of employee performance before AI case. So note here I have marked out the bonus effect that is what the reward scheme is already doing on the employees. And then once we introduce AI, it has nothing like too extraordinary impact on the HS type. But then on the LH and the LL type, because they are the ones who will be helped by the AI most, and they can improve their productivity. And we call this improvement the learning effect of AI. It will be experienced by both the LH and the LL type. And then, because right now we know that the LH type is going to be the one who can receive bonus. So they will have more motivation to work harder in order to keep the salary, the bonus. So we call this the competition and the motivating effect experienced by the LH type. Then on the other hand, the HL type instead will be demoted to the third place, and therefore they will experience this demotivating effect. And as we can see, there are kind of 3 different types of components in terms of AI's impact, right? And 2 positive effects and 1 negative one. So which means depending on different parameter regions, or depending on the nature of the business and their employee composition. For example, when the skill gap between the low type and high type is not very different, the size of the positive effect is going to be small. And then when the LH type is accounted for a larger portion among all the employees, then it means the negative effect is might be dominating the overall impact. So that's why we could see a productivity and the profit drop for the firm even after we're using AI. So what can firm do, right? We cannot just stop here. And so we want to see if we can provide some suggestions on what the firms can do. And following that breakdown, a natural response is, can we do something to just remove that negative demotivating effect? And then even more natural response is, okay, maybe we can just guarantee the reward so that the employees won't feel demotivated. And for example, the firm can see that we will make sure that everyone will receive the same rate as they do before. But however, we find that this type of reward policy is not going to help at all. So the profit is going to be still lower than the pre-AI case. And it's also going to be lower than the after AI case under the normal no guaranteed policy. And the intuition is actually still related to the motivation among the employees. because once the salary is guaranteed, the employees, they don't really have the incentive to compete in order to keep their bonus, right? So clearly, this first option is not the best revenue out of this case. Then what's the second option? So recall that this type of interaction happens because the flip happens. So that's why we think it's possible that the firm can just use a less effective AI, as shown here. If instead of choosing a more expensive AI product, it can choose a slightly less effective one and avoid the flipping among the employees' performance, and therefore achieve the higher profit. But however, as you can see, this is still not the best we can do, right? Because if somehow we can find another option out and remove the demotivating effect, we could extend that profit beyond this current highest possible level and achieve an even better one. So that's why right now we are thinking of whether the firm can do something else, such as strategic hiring. That is, the firms can proactively maybe change the composition of their employees so that they can do something better. And I think it's the end of the talk, so just quickly summarize. We model how AI interacts with the employee incentives and the most common promotion policy. And we find there can be a demotivating effect. And so we have considered quite a few remedies. And the third one, like strategic hiring, is something we're still working on. And so here's the end. And if you want to stay tuned to our research, please scan this QR code. So thanks, everyone. And I'll open to question now. Yes.
How did you measure the tangible versus the intangible skills?
That's a good question. I think one thing I want to clarify is in our analytical model, we don't specifically to distinct. The thing we are considering is like at the conceptual level, there will always be tangible versus intangible. So the insight from our paper is more of a kind of a framework that firms can use to consider when they are, let's say, before they adopt AI, they can evaluate what's going to be their AI system's impact on their tangible skills versus intangible. But indeed, our paper doesn't provide a guidance in terms of what is specific tangible versus intangible. But it would be great to do something solely in that line.
So when you measured the improvement in performance, right, for some select groups, you looked at their job role, like this role has mostly tangible versus intangible skills. Like, how did you measure, like, which group
So I think just quickly go back. Yeah, so basically here, I have one thing I want to clarify is this case is only one of the possibilities that can happen to the case. So, which means there will be other cases, but it's kind of just less interesting, so we didn't report here.
Let's take other questions offline, and we'll start the panel at about 11 o'clock.